Let's take a look at a second algebraic method for solving systems. Now, it's not that substitution won't always work. It will, but there are times when substitution can be really, really painful to use, many times as a matter of fact, where elimination method might be a better choice. Right? I use substitution method when one of the variables is already solved for, or it's very easy to solve for one of the variables. I use elimination method basically all other times. Right? So the elimination method is, like I said, another algebraic method where we don't have to graph. We're just going to use our algebra skills to actually solve the system, find the solution to the system, the ordered pair that works in both equations. All right, well, in the elimination method, our first step is to always make sure things are lined up column-wise. So the x's under the x's, the y's under the y's, the equals under the equals, and the constants under the constants. So let's just say make sure. All like terms. Let me just put in the parentheses and the equals also. Make sure the equals are lined up. So the x's under the x's, those are like terms. The y's under the y's. Equals need to be lined up. They're not like terms, but equals and your constants. So make sure all like terms and equals are lined up column-wise. Just make sure they're underneath each other. If they're not, you can move terms around on either side of the equation to make that happen. So most of the time, if I'm going to use elimination method, this is already done for me. So in this case, yeah, we're good. X's, Y's, constants, and the equals, they're all lined up. Okay, now in step 2, this takes a little bit to describe, but the idea is, I think the concept is much easier. So we're going to say multiply one or both equations. Put that in parentheses. One or both equation or equations, plural. Multiply one or both equation or equations by some number or numbers, if you're multiplying both equations, such that when the two equations are added, you say one variable eliminates, hence the name, elimination method. So one variable is eliminated. Phew. It's a lot of words for something that's really not that difficult to explain here. If I were to add these two equations right now, not doing a thing to them, we'd get 4x plus 5x. That adds up to be a 9x. Negative 3y plus 2y adds to be a negative y. And 25 plus 14 gives us what? 39. So the equation 9x minus y equals 39 doesn't help me. Right? The idea is I don't want a third equation that has two variables to it. So we're going to be a little bit more clever about this. The idea is, yeah, we're going to add these two equations together. X's for x's, y's for y's, and constants for constants, and come up with a new equation. But that new equation is going to have one of the two variables missing, either the x or the y. And we're going to make that happen through what's called the elimination method. That is, we can and we are allowed to multiply both sides of any equation by any number we wish, other than 0, of course. You want to avoid doing that. So we think, well, if I add these two together right now, I get 9x. But I could make that a 20x, and I could make that a negative 20x very easily. If I multiply the top equation by 5, and the bottom equation by -4, I would get a 20x and a negative 20x, and those would cancel out. Now, there's other numbers I could use. Like, for example, I could pick another number here, say 10. I could multiply the top equation by 10 and make a 40x, and the bottom equation by a -8 and make a negative 40x, and that would work as well. But I'm looking for the smallest number. So I'm really looking for the least common multiple of 4 and 5. So the smallest number that 4 and 5 divide into would be 20. Right? So I can make one a 20, the other the opposite of 20, so a negative 20, just by multiplying by a negative. Well, we could also do that to the y's. If you look at the numbers 3 and 2, the least common multiple would be 6. So I can multiply the top equation by 2 and the bottom equation by 3, and that would also accomplish a negative 6y on the top and a positive 6y on the bottom. When I add those together, the y's would eliminate. Right? Now, it's going to change the numbers in the rest of the equation, but I'm not worried about that. I'm just trying to eliminate either the x's or the y's. Now, as far as what's going to be easier here, I'm thinking getting rid of the y's is going to be easier. So what I'm going to do is I'm going to multiply the top equation by a positive 2. I don't care that that's going to be an 8x. It will. And I don't really care that that's going to be a 50, though it will. What's going to happen is I'm going to get a negative 6y here. And likewise, for the second equation, I want a positive 6y. I want the opposite of what I just created up here. So the opposite would be a positive 6y, so I need a 3 multiplied by 2. Yeah, it's going to make a 15x, so what? And yeah, it's going to cause it to be a 42, so what? I'm just worried about the y's being eliminated. So in the top equation, I get 8x minus 6y equals 50. Multiplying the top equation by 2. It's the same as the original, it's just got bigger coefficients. It's the same. If I put this in slope-intercept form, it would be the same as that in slope-intercept form. They're the same equations, it's just these have bigger coefficients. Likewise here, as long as I multiply both sides by this 3, everything gets multiplied by 3. I have not changed the equation. And then 3 times 14 is 42. Right? So these two equations are the same as the original, it's just these will eliminate the y variable when I literally add these up. It's like one giant addition problem. So 8x plus 15x is 23x. The y's eliminate, that's the whole point, equals, what is that, 92. All right, so multiply one or both equations by some number of numbers such that when the two equations are added together, one variable is eliminated. Step 3 is pretty easy. Since one of the variables is eliminated, you solve that very easy equation. So we're going to just simply divide both sides by 23. So that's solve the equation you get. So divide by 23. 23 goes into 92, I believe, 4 times. This one comes out nicer. Now, once you have one of the variables, you find the other variable not through your substitution that we did on the substitution method where you have a nice expression with just that one variable in it. You have your choice of equations. You can pick any equation that you work with. So this 4x minus 3y, 5x plus 2y. You can even go to 8x minus 6y or 15x plus 6y. Any of these equations, when you substitute 4 back in for the x, should be able to give us the same y variable. Right? So solve equation and resubstitute. Solve variable into any of the equations. To find other variable. Again, it doesn't matter. Just pick an equation. 5x plus 2y equals 14 looks pretty easy. So 5x, substitute in 4, plus 2 times y equals 14. And you can see you just have to solve this equation. So that's 20. We'll subtract it from both sides. Just kind of move this problem along. 14 minus 20 is negative 6. Divide that by 2. And you get negative 3. So our solution to the system, right, as the ordered pair 4, negative 3. And we solve the system through elimination. Right? That's the idea here. Okay, let's try one other just because it comes out to be a special case here. I should have done that spoiler alert. Let me make sure I copy it right this time. You saw what happened in that last video. 18 and negative 3x plus 2y equals 10. Okay, so say we have a system like this. Looks like it's ready-made for the elimination method again. And just make sure all the terms are lined up column-wise, which, yeah, we're good. It's going to happen most of the time where we're okay with this. All right, next, we can get rid of the x's, or we can get rid of the y's. Since we did the y's in the last one, let's get rid of the x's. So we're looking at the least common multiple of 6 and 3, and that is 6 itself. So some might be thinking, well, what about 12? What about 18? Those are common multiples, and it will work, but I think the easier one would just be a simple 6. So if I just take the bottom equation and multiply it by a 2, you can see I'm going to get a negative 6x. When added to 6x, we'll cancel. What happens the rest of the way? Don't care. So let's group these together. I get 6x minus 4y equals 18. And negative 6x, just taking this 2 through, plus 4y equals 20. Adding these two together, the x's eliminate. That was the whole point. But take a look over here. The y's also eliminate. That can happen. I get a big 0 on the left side. On the right side, I get 38. Now, this is something different. Everything we saw before has been consistent and independent. That means you get exactly one solution. Two lines are intersecting at one point. Here, what we have is a situation where it's one of the weird ones. It's either consistent dependent, they're the exact same line, or it's what we call inconsistent, which means the lines are parallel. Now, we can check by looking at slope-intercept form, and we can know, or just take a look at your final equation. If the final equation makes sense, like 0 equals 0, that would be consistent dependent, which means they're the exact same lines. But this equation makes no sense. 0 equals 38, that's 100% false. I don't say my solution is false. I say I have no solution, or a one-word statement would be inconsistent. So just like with graphing, you can come up with these weird sort of things, consistent, dependent, inconsistent. Definitely happens when you solve with algebraic methods as well. Just be prepared for them.